Welcome to the Planck's constant lab. The goal of this lab is to measure the IV characteristics of various LEDs and then relate, using Planck's constant, the energy of a photon to the actual voltage drop across the LED. The setup, electrically speaking, is fairly simple. I have a power supply just out of the frame here, which produces a variable voltage from 0 to 30 volts. This is the positive lead from the power supply, which goes through an ammeter in series. The output from the ammeter then goes to a resistor, a dropping resistor, about 330 ohms in this case, and then to an LED, and current returns via the black wire. So here is the simple series circuit for the LED. This meter measures current, therefore. This meter is a voltmeter, and it's located directly across the terminals of the actual LED itself. It displays the voltage across the LED device, but not necessarily right across the junction, since there's electrical losses within the semiconductor itself. The experiment itself is fairly simple. We start by varying the voltage across the entire circuit to get a current of approximately 1 milliamp. And if I vary this slightly, I get 1.06 milliamps on the meter. I then measure the voltage across the junction as 2.424. Next, increase the current, the voltage rather, so that the current in turn increases in approximately 1 milliamp increments. Now, it's not necessary that they be exactly 1 milliamp, 2 milliamps, 3 milliamps. Since we're going to graph this on Excel, as long as we get close, we're fine. We need 10 points approximately 1 milliamp apart. So in this case, 2.09 milliamps, 2.654 volts. And we simply increase the current accordingly, writing them down each time, plugging them into Excel. Now, as the current increases, the voltage also increases across the LED device. This isn't necessarily true with an ideal diode. With an ideal diode, no matter what the current is, we expect the voltage to be about the same. But for a real device, there are electrical resistances within the device itself which lead to this characteristic curve. And in a few moments, we'll look at how to analyze that. When observing the LED, we see the characteristic output. In this case, it's colored green. However, when we use a diffraction grating in front of the camera, something else becomes evident. Notice how our green LED does put out an awful lot of green radiation. However, at the same time, the radiation extends to the blue. You can see the blue streak over here, and into the red and orange areas as well. So an LED is not exactly a monochromatic device. While it may look green to you and me, and there's certainly more output in the green than in any other region of the spectrum, there's also output extending off in either directions. In the case of red emissions, this side of the spectrum, we don't expect that, since that would infer automatically that there are transitions occurring within the band gap. However, the reality is there's impurities inside that gap, and so you're going to get longer wave photons than expected. In the case of the shorter wave photons on the other side of the spectrum, this is expected because the charge carriers extend off in both directions, the holes extending and the electrons extending from the other band. So there are a large range of expected output wavelengths. Now, at a current of approximately 10 milliamps, the voltage across our LED is 2.983 volts. This is a fairly high voltage, and it corresponds roughly to the number of electron volts of the actual photon being emitted. Of course, we have some compensating to do for the electrical resistance of the device, which will be done during the analysis. If I substitute a different color LED, and in this case, I'm going to use an yellow LED, I get a lower voltage, 2.064 volts. Completely expected, since the photons of yellow light have less energy in them, and therefore the band gap is smaller. Substituting yet another LED. I picked the same color. This one, I get 3.024, meaning that the photons have more energy than a green LED, and therefore we expect a shorter wavelength. With the points already loaded into Excel, we now wish to graph them as a series of X and Y points. In reality, the voltage will be on the x-axis, while the current will be on the y-axis. We do this because we want to extrapolate to the point where current is 0. That will automatically remove any of the effects of impurities within the band gap itself and give us a true indication of what the actual band gap voltage is. So, using Excel now, we go Insert, and we want a graph like this. And this is the completely wrong graph because this one has current on the y-axis and it has voltage on the x. So what I'm going to do now is eliminate this graph and start again. Insert graph. Now I want to be able to select my own data this time. So I can either select the data from there or using that icon. I'm going to add a series to it. I'm going to call it green LED. The X values again are voltage. It's incredibly important that we do this or the graph is going to be backwards. And now I'll select my Y values over here. And there we go. We now have a nice graph. Now the graph itself is crowded in over here, and it really doesn't do anything for our analysis to have it crowded. So we're going to take our axis over here, we're going to format it, and we're going to change the minimum to about 2 volts, just to zoom in a little bit. There we go. So, how to analyze this? What we want to do is draw a trend line through this, and we want to draw it through the linear portion of the actual curve itself. In other words, I only want it going through this portion here, and I don't want it going here. The worst thing you can do is take an entire piece of data now and draw a trend line through it. It'll intercept somewhere over here, but this part, remember us talking about this in the lab, that shouldn't even be there. A lot of that is a low voltage across the band gap, which just isn't really there. It's caused by things like, for example, the impurities inside the semiconductor itself. So what I want to do is take the actual LED curve and find the linear portion. If I hold up a ruler to it, or some other object, I can see that 1, 2, 3, about the last 6 points are about linear. This is certainly not linear, and this is way off. So I'm going to want to draw a trend line only to those 6 points. There's a number of ways you can do this, but let me show you one of the easiest ways. I'm going to click inside the graph again, and I'm going to select data. This time I'm going to select a second data. I'm going to call this trend line. My X values are going to be, as I said, the last 6. So 1, 2, 3, 4, 5, 6 values. And I'll select the Y values the same way. 1, 2, 3, 4, 5, 6. And as expected, I get a second line right on top of the first ones. Now, if I click on that line itself, right-click, and say add trend line to it. I'm going to add a trend line to those. You can't see it because it's literally right on top of the actual data itself. I want to display it on the chart, y equals mx plus b. Very important that I do that because now I can solve for y equals 0, and that'll allow me to find the point at which it intercepts over here. So mathematically, I've done everything I need to do. It doesn't quite look right though, because we expect this graph to intercept somewhere down here. So what I'm going to do is set this backwards, about 5, oopsie, let me go backwards here, maybe 2. There we go. 1 period backwards. And that'll allow me to see where the actual line intercepts right there. Now, once again, I can take my x-axis and I can format it to get rid of all of the stuff on it. I certainly don't need to go into the negative. That makes no particular sense. So if I go to this axis and I format it, I can then put 0 in here. And there we go. Now you can see easily where this contacts. You expect, once you've solved y equals mx plus b, you put in for 0, and you solve for x, you expect to see approximately 2.7 something volts. And that is the actual forward voltage across this gap for this particular LED. This has to be done with every single LED. Now, one of the temptations people have is to put all of them on one graph, which works fine, but remember that the x values are not the same and nor are the y's. You cannot have them line up. Each graph has to be done as an individual series.